Okay, this is our cartoon of the classical complement pathway. So here's our little bacterium, which is a singular for bacteria, just coming in to infect us. Now, remember that the classical complement pathway is really the first time that we're getting to see the adaptive and the innate immune responses working together. And the reason for that is that it's mediated by antibodies, okay? So this is either far enough along into the immune response that we've already made antibodies, so about 10 days, or we've already seen this pathogen before, so we already have antibodies to it. Regardless, the first thing that's going to happen is that our C1 molecule is going to come in and bind to the FC portions of two of those antibodies. Now, currently C1 is kind of in its off form, right? The serine proteases, C1R and C1S, are hidden. But when it binds to two or more antibodies, it undergoes a conformational change, exposing these serine proteases. And it's these serine proteases that are going to go on and cleave the molecules of the complement pathway, kind of setting up this cascade. So the first substrate for C1 is C4. So C4 comes in, gets cleaved by C1, and you wind up with C4A and C4B. Okay, now C4B is going to covalently bind to the surface of our antigen. C4A is going to float off into solution. After that, C2 is going to come in, and it's going to be covalently cleaved by the C1 molecule. And then you're going to get C2A this time that's going to covalently bind to C4B, and C2A will float off into solution. This molecule, C2A, C4B, is called the C3 convertase. And from that, you can probably guess that it is capable of cleaving C3. So at this point, you'll get C3b and C3a. Now remember, this is a step of tremendous amplification. Enzymes are great at amplifying reactions, and a single C1 molecule over here can probably create about 10 or so C3 convertases in the local area. But a single C3 can actually cleave 1,000 C3 molecules like in a minute. So, or actually in a per second. And the enzyme is active for about 2 minutes. So you're going to get a lot of C3b. And this is really important because the most important thing, are you hearing me? I wrote it in the notes too. The most important thing about the classical complement pathway is the creation of C3b. This is because C3b is a fantastic opsonin. In this way, antibody and complement work together to create the greatest possibility of phagocytosis of the antigen by our phagocytes, our neutrophils and our macrophages. This is the greatest possibility we have to kill the pathogen inside one of our phagocytes. If one of the C3bs happens to land near our C2a and C4b, you get what's called the C5 convertase, and you can probably guess that that's because it's able to cleave C5 into C5a and C5b. Now, that's pretty much the end of the enzymatic reactions, and now we're going to move on to what's called the common final path. This is the pathway that actually leads to formation of the membrane attack complex, and it's shared by not just the classical complement pathway, but also the alternative and lectin-based pathways. Now remember, there are 3 complement pathways: classical, alternative, and lectin. And really, the only thing you need to know is that they start differently, and they all end the same with the membrane attack complex. I mean, that C3b is the most important thing about complement because it creates opsonization. So we cleaved C5 into C5b and C5a, and what happens is C5b goes out and binds to C6, C7, and C8. C6, C7, and C8 can actually cross the membrane of the bacterium here. And in most cases, that's going to be enough to cause the bacterium to lyse. But in some cases, you might need the addition of C9, which is this tubular looking thing here. So you'll get several C9 molecules, on average about 6, that will come together to form this tube, which literally like punches holes into the membrane of the bacteria, which, you guessed it, also causes it to lyse. So the end result is that the bacteria is dead. This is exceptionally effective against many gram-negative bacteria, Neisseria in particular, which causes meningitis and gonorrhea. It's not as effective against gram-positive bacteria, which tend to have a thicker cell wall, which makes it more difficult for C9 and C6, C7, and C8 to actually penetrate. And that's the classical complement pathway.